tapping from the top of the main breaker lugs is generally acceptable if certain conditions are met. Firstly, the main breaker lugs must be rated for the total current of the tapped load plus the existing panel load. Secondly, the wire size of the tap must be adequate for the current draw of the tapped load. For example, if there is a 60 amps main breaker with 8 branch breakers, the panel has a total capacity of 100 amps. If the rectifier and elevator motor draw less than 40 amps, which is 100 amps minus 60 amps, then it is acceptable to tap from the main breaker lugs. Several alternative methods exist for feeding the rectifier. One option is to install a separate subpanel with a dedicated feeder from the meter. This provides isolation and protection for the rectifier and elevator motor. Another option is to use a motor control center, often abbreviated as MCC. Motor control centers are designed to provide power and control to multiple motors. One could install a motor control center to house the rectifier and elevator motor starter, with a separate feeder from the meter. If the incoming service is single-phase, a transformer could be installed to convert the power to three-phase and then use a separate rectifier to supply the elevator motor. Several considerations are critical. Safety is paramount. Ensure that all wiring and connections are made in accordance with the National Electrical Code, often abbreviated as NEC, and applicable local codes. Accurately calculate the current draw of the rectifier, elevator motor, and any other potential loads that will be connected to the tapped circuit. Consider using isolation transformers to provide additional protection for the rectifier and elevator motor from voltage fluctuations and power surges. Plan for regular maintenance and testing of the tapped circuits and connected equipment to ensure reliability and safety. Consider the following points when tapping from main breaker lugs or exploring alternative feeding methods for a rectifier powering an elevator motor. The National Electrical Code, or NEC, provides guidelines for electrical installations to ensure safety. Article 240.21 addresses the protection of tap conductors. It outlines the requirements for the overcurrent protection of conductors that are tapped from a feeder or branch circuit. The length of the tap conductor is a critical factor. Shorter taps generally have fewer restrictions. For example, a tap conductor not over 10 feet long is permitted under specific conditions, including being enclosed in a raceway and having an ampacity not less than the combined calculated loads on the circuit supplied by the tap conductors, and not less than the rating of the overcurrent protective device at the termination of the tap conductors. If the tap conductor is longer than 10 feet, but not more than 25 feet, different rules apply. The tap conductor's ampacity must be at least 1/3 of the rating of the overcurrent device protecting the feeder or branch circuit from which it is tapped. The tap conductor must terminate in a single circuit breaker or set of fuses that will limit the load to the ampacity of the tap conductor. The tap conductor must be protected from physical damage and enclosed in a raceway. For taps longer than 25 feet, more stringent requirements apply, often requiring overcurrent protection at the tap point. When calculating the load, consider the continuous and non-continuous loads. The NEC defines a continuous load as one where the maximum current is expected to continue for 3 IOs or more. Overcurrent devices protecting feeders and branch circuits supplying continuous loads must be rated at not less than 125% of the continuous load plus the non-continuous load. This ensures that the overcurrent device does not trip unnecessarily due to prolonged high current draw. For motor loads, the NEC specifies different requirements for overcurrent protection and conductor sizing. The motor's nameplate current rating is used to determine the conductor ampacity. Conductors supplying a single motor must have an ampacity of not less than 125% of the motor's full load current rating. The overcurrent protection for motor circuits is designed to protect the motor from overloads and short circuits. The NEC allows for the use of inverse time circuit breakers, fuses, and motor overload relays. The rating or setting of the overcurrent device depends on the motor's type, horsepower, and starting characteristics. The motor's nameplate should be consulted for specific information. Article 430 of the NEC provides detailed requirements for motor circuits. When dealing with rectifiers, it's important to consider the harmonic currents that they can generate. Harmonic currents are non-sinusoidal currents that can cause voltage distortion and overheating of electrical equipment. Harmonic filters may be required to mitigate the effects of harmonic currents. The size and type of filter depend on the rectifier's characteristics and the electrical system's impedance. Isolation transformers can provide several benefits. They can isolate the rectifier and elevator motor from voltage fluctuations and power surges. They can also reduce the flow of harmonic currents into the electrical system. Isolation transformers are available in various voltage and current ratings to suit different applications. A separate subpole provides several advantages. It isolates the rectifier and elevator motor from other loads on the main panel. It provides a dedicated overcurrent protection for the rectifier and elevator motor. It simplifies maintenance and troubleshooting. The subpanel should be sized to accommodate the rectifier and elevator motor's load, as well as any future loads that may be added. A motor control center is a centralized enclosure that houses motor starters, overcurrent protection devices, and control components. Motor control centers are commonly used in industrial and commercial applications. They provide a convenient and organized way to control multiple motors. Motor control centers can be custom designed to meet specific application requirements. Grounding is a critical aspect of electrical safety. The NEC requires that all electrical equipment be properly grounded to provide a path for fault current to flow back to the source. This helps to protect personnel from electric shock and minimize the risk of fire. The grounding system should be designed and installed in accordance with the NEC requirements. Regular maintenance and testing are essential for ensuring the reliability and safety of electrical equipment. Maintenance should include visual inspections, cleaning, tightening connections, and testing overcurrent protection devices. Testing should be performed by qualified personnel using appropriate test equipment. Records of maintenance and testing should be maintained for future reference. When working with electrical equipment, it is important to follow safe work practices. These include energizing equipment before working on it, using appropriate personal protective equipment, and following lockout/tagout procedures. Only qualified personnel should perform electrical work. Here are some additional considerations for tapping from the main breaker lugs or exploring alternative feeding methods for rectifier powering an elevator motor. Firstly, voltage drop. Calculate the voltage drop from the source to the rectifier and elevator motor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC provides guidelines for voltage drop in branch circuits and feeders. Secondly, coordination of overcurrent protection. Ensure that the overcurrent protection devices are properly coordinated to minimize nuisance tripping and selectively clear faults. This means that the overcurrent device closest to the fault should trip first, while upstream devices remain closed. Thirdly, future expansion. Consider the possibility of future expansion when designing the electrical system. It may be necessary to install a larger subpanel or motor control center to accommodate future loads. Fourthly, energy efficiency. Consider using energy-efficient motors and rectifiers to reduce energy consumption and operating costs. Energy-efficient equipment can often pay for itself over its lifespan. Fifthly, local codes and regulations. Ensure that all electrical work complies with local codes and regulations. Local codes may have more stringent requirements than the NEC. Sixthly, professional consultation. Consult with a qualified electrical engineer or contractor to ensure that the electrical system is properly designed and installed. A professional can provide valuable insights and recommendations. Seventhly, documentation. Maintain accurate documentation of the electrical system, including drawings, specifications, and test reports. This documentation will be helpful for future maintenance and troubleshooting. Eighthly, training. Provide adequate training to personnel who will be operating and maintaining the electrical system. Training should cover safe work practices, troubleshooting, and maintenance procedures. Ninthly, emergency procedures. Develop emergency procedures for dealing with electrical problems such as power outages, equipment failures, and electrical fires. These procedures should be clearly documented and communicated to all personnel. Tenthly, insurance requirements. Check with the insurance company to ensure that the electrical system meets their requirements. Insurance companies may have specific requirements for electrical installations.